Good afternoon, everybody. I hope that you're having a great day. Um, I have completed recording all of your lectures for tomorrow and Friday, in order to make it a little bit more kind of digestible. Um, and hopefully this will help out in narrowing your focus and narrowing your scope of what you're looking at. Um, One thing that I did was I went through the learning objectives on our Canvas page and made videos for each one of those respective learning objectives. Um, if you go to our Canvas page and look on Friday, you'll see where the recorded lecture is or where that link is. If you click on that, that will take you to the place where all of the links for the videos for sugars are. At the moment, where is PowerPoint? PowerPoint is, I tried to open my file. Okay, there we go. I have your exam grades posted. I just added those to Canvas a little while ago. Um, the For those of you who took the exam in person, I have a copy of the exam that I'm going to post, and I will distribute as well as a key so that you have a reference point. And I should have that, midday tomorrow or so. um, and today I remember we were going to start on around slide 30. Yesterday we covered a lot of material and we kind of did a lot of different things with respect to that bulk of different material. We covered basically mechanisms and sequences in which substrates bind. So when you have a multi-substrate reaction, you have your ordered, your random, and your ping pong mechanism. One of those, the ping pong mechanism, has a unique form of an enzyme. Then we also got into mechanisms in terms of like Gen Chem, or sorry, not Gen Chem 2, but instead mechanisms in terms of like organic. Where are electrons being pushed? And where are they starting from? And what species is involved? Um, and that's kind of where we're going to continue today. Blow this slide up and share my screen. Throw the chat down there. Share my screen. There we go. And some other minor adjustments, and then I'm ready to go. Okay, so yesterday we talked about acid-base catalysis, and with respect to acid-base catalysis, what we went over was proton transfer, and we talked about general acid catalysis, general base catalysis, as well as concerted acid-base catalysis. Now, when it comes to that concerted acid-base catalysis, what is going on, man? Okay, just a second. I got to stop my share. I didn't ask to open a web browser. Um, when it comes to acid-base catalysis, PowerPoint's giving me fits right now. But it will shake it out in just a moment. Getting there. Oh yeah, there we go. It quit completely. So now I'm gonna reopen that file. When it comes to acid-base catalysis, think about your classical definition of an acid. Think about your classical definitions of a base. An acid is something that can donate a proton. A base is something that can accept a proton. When it comes to amino acids that can act as acids or bases, respectively, a good amino acid to act as an acid is histidine. A good amino acid to act as an acid is arginine or lysine. Those are great candidates to act as acids because at a neutral pH, they're going to have a proton. Aspartic acid and glutamic acid. Chances are, with their R groups and their pKa values of those R groups at about 2 or so, those are going to be better bases at a neutral pH for that same reason. Now, I showed you guys this slide right here that shows our amino acids and what they look like when they're acting as an acid and what they look like when they're acting as a base. And I want you to remember that terminology, acting as or behaving as. I want you to use that. And the reason for that is there are some amino acids that can act as an acid. They can also act as a base. Now, when we looked at the pH profile, this right here, our y-axis represents enzyme activity, and our x-axis represents pH. We're starting at a pH of, let's say, 1, and it goes all the way up to 14. Now, this is very generally. Our enzyme activity is 0 all the way up to 100. The curvature of this line, I don't want you to look at that and think to yourself, it's a sigmoidal curve. Must be something about cooperativity. That's not what we're talking about in this instance. Instead, what we're talking about here is you could treat this almost as relative. At a low pH, if an enzyme has a general base mechanism or it has a residue that's acting as a base, at a low pH where there's tons of protons, this is not going to have very high activity. Whereas at a high pH or a higher pH, a general base is going to have more activity. Meanwhile, an amino acid or an enzyme that is acting as a general acid, it's going to have its highest activity at a lower pH. So the question is, does the amino acid within the active site, the critical amino acid, is it protonated or deprotonated? And let's say that you have an aspartic acid or an aspartate. Well, if that amino acid is protonated, but it is supposed to be acting as a base and accepting a proton, this group has a pKa of about 2. Let's say 2 point, actually no, the R group is going to be about 3.1. If this is in a solution with a pH of 2, but this supposed to act as a base, will it act as a base at a pH of 2? Give me a yes or no in the chat. Yes, it will work just fine, or no, it will not. It will not. The reason that it will not is because it's protonated. It is acting as a base. It cannot accept another proton. Or it's trying to act as a base, I'm sorry. Now, this next curve right here, our bell-shaped curve for enzyme activity, we have enzymes that follow an acid-base catalyzed mechanism, they've got a range in which they're going to display their highest activity. This might be between 9 and 9.5. It depends. What that means is that if the pH is above 9.5, that enzyme's going to be pretty inactive because it's too basic of an environment. If the enzyme is in a pH solution in a solution with a pH of 8, it's also going to be inactive because it's too acidic of an environment. Now, can I get a yes, I follow everything about acid-base catalysis if you follow everything about acid-base catalysis, or no, I don't follow, and I've got some confusion about it? Sorry, I meant to add it to the chat. Okay. Well, this is a hypothetical. So this is a hypothetical just saying that any enzyme is going to have a range where it's at its optimal activity level. This could be between 9.5, it could be 3 to 11. It just depends on the makeup of the residues within the active site. Okay. Um, I'm going to go ahead and proceed. If you have questions, please don't hesitate to ask me. If you have confusion with respect to acid-base catalysis, I think a really good thing for you to kind of begin anticipating is to look at these definitions: general acid catalysis, general base catalysis, and ask yourself the question, which amino acids, which amino acids can act as a general acid? Which amino acids are good candidates to act as a general base? So think about which amino acids can accept a proton, which ones can donate a proton. Then ask yourself the question, well, what does it look like? So if I was talking about any one of these amino acids, cysteine's a good candidate. If if I were to draw a cysteine residue that looks like this, and I said, hey, this amino acid, this cysteine right here, is in the active site of a acid-base catalyzed reaction. In this state where I put this star, it's going to act as a general base. It's going to accept a proton. I would want you to say, no, it's not, because it's already protonated. It's simple. It's a simple rule, but it's kind of tough to wrap your mind around it. So acid-base catalysis is one of our models for enzymes to catalyze a reaction. Another model is known as covalent catalysis. In covalent catalysis, a covalent bond is transiently formed. So at the heart of covalent catalysis is the formation of a covalent bond. That bond is formed between our substrate and the enzyme, or a coenzyme. This reaction usually involves a nucleophilic group on the enzyme. Okay, so we need a nucleophile on the enzyme and an electrophile on the substrate. Now, thinking about a nucleophile, you might say, oh man, it's been a minute since I thought about nucleophiles and electrophiles. But I always think about a nucleophile as something with a partial negative charge. That's the easiest thing for me to think of. Here, what we have is a model for a enzyme catalyzed reaction. This enzyme is known as chymotrypsin. Chymotrypsin, the enzyme, what it does is it breaks peptide bonds. Now, what chymotrypsin is going to do mechanistically is it is going to have an active site serine. So the amino acid serine is an amino acid within the active site of chymotrypsin. Now, this this serine residue, well, serine's protonated. Okay. But this chymotrypsin has another amino acid that has a lone pair of electrons within the active site. And what it is going to do is it is going to use that lone pair of electrons to pluck that hydrogen off of serine, which makes serine a really fantastic nucleophile to attack the electrophilic group on our substrate. Okay, so if we want to, I think that it's helpful to name these out. Here's our nucleophile, and here's our electrophile. So the nucleophile in a covalent catalyzed reaction is on the enzyme, or is a amino acid within the enzyme. The electrophile is a part of the substrate. Now, what's going to happen is whenever that nucleophile attacks that electrophile, we've got some electrons that are going to be pushed around. And when those electrons are pushed around, we break this bond right here. And if somebody adds to the chat the correct answer for what that bond is, there's a bonus point on the next test. That bond, and you have to get it right. So if you want to send private messages to each other, that's fine. This bond, and before anyone answers, do not answer. Do not answer. Okay. We have chymotrypsin, which cuts proteins. Okay. We've got NC. Okay. Now think about a protein. Proteins look like this: NCC, NCC. Okay, there's a dipeptide. Um, does anyone see those elements in there? Totally, you do. I know that you do. But this right here is a carbonyl carbon. What I am looking for in the chat is for somebody to answer correctly. And you can send me a private message if you are certain of it. What is the name of that bond? The specific name of that bond. It's high stakes. High stakes, but not super high. I'll give you a hint. The name of the bond starts with a P. Oh, 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 private messages coming through. Yup, 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 yup. Oh. The first response that I got from one of your classmates was peptide. You're absolutely correct. So, for the people who privately messaged me peptide, good job. You got everyone in class a bonus point on the exam. So, good job, everyone. So, a protease cuts peptide bonds. And in order to do that, covalent catalysis is employed. So, this is a peptide bond. And this is a little bit funky because, well, it's this same image, but kind of backwards. Okay. Now, which amino acids are great nucleophiles or can act as nucleophiles? Well, if something has a hydroxyl group, a sulfhydryl amino, or an imidazole group. The nucleophilicity of a substance is related to its basicity. Biologically important nucleophiles are negatively charged or contain unshared electrons. So our hydroxyl group, yeah, it can work well. It can form a really strong nucleophile. All of these are really good nucleophiles. Now, the amino acid that this one is right here, this would be a histidine ring. Imidazole is the name for a histidine, or is the name of the ring that is found on a histidine side chain. Electrophiles. Biologically important electrophiles generally are either positively charged or contain unfilled valence electron shells or contain an electropositive atom. Now, what did we see in this right here? What we saw was none other than a carbonyl carbon atom. That was our electrophile. There will be some questions. There could be questions on your quiz tomorrow or on your exam that ask you, what is this? Is this a nucleophile? Or identify the nucleophile, identify the electrophile. And you'll have labels like A and B or something like that. Okay, so the key at the heart of a covalent catalysis, or at the heart of covalent catalysis, is the formation of a covalent bond between the enzyme and the substrate. Metal ion catalysis is our third and last type of catalysis. Metal ion catalysis, nearly 1/3 of all known enzymes require the presence of metal ions for catalytic activity. Now, metalloenzymes will tightly bind metal cofactors like Fe2 plus 3 plus, Cu2 plus, Zn2 plus, Mn2 plus, or cobalt 2 plus. Okay, so these are metal enzymes. Metal activated enzymes, slightly different definition. The key difference is basically how much they grab onto these. Metalloenzymes tightly bind to metals. Metal activated enzymes, by comparison, they grab onto them a little bit loosely. The ions that they use are sodium ions, potassium, magnesium, and calcium. Smaller molecular weight ions. Now, a cofactor is generally referred to as, sorry, If you ever hear the term cofactor, you're generally referring to a metal ion, whereas if you hear coenzyme or co-substrate, you are referencing a organic molecule. If you have ever heard an apoenzyme or haloenzyme, well, an apoenzyme is the inactive form of the enzyme. So the cofactor is not there. And a haloenzyme is the form of the enzyme with that cofactor present. Okay, so those are our three different types of mechanisms. Now we're going to look at a couple of them. Here's ribonuclease A. I'm going to come back to that. This is carbonic anhydrase, our old friend that really likes to take water and CO2. And then last but not least is lysozyme. Okay, so we're doing these in a little bit of a different order. And I'll highlight some of the things that I want you to know about this. Whenever we are looking at a mechanism, you start up in the upper left-hand corner. What you're looking at is basically your starting point. In the middle here is our RNA molecule. We've talked about ribonuclease A. We talked about it because this is the enzyme that Christian Anfinsen used to look at how proteins fold and unfold. What ribonuclease A does is it takes an RNA molecule, a single-stranded RNA molecule, and chops it up. Now, how does it do it? Well, it uses two amino acids. Those two amino acids are histidine and histidine. Now, I highlight these two histidine residues, and I'm going to make sure that you understand that these two amino acids are not free-floating amino acids in solution. They are a part of our protein. If I remember, ribonuclease A is something like 136 amino acids long. So the primary structure is 136 amino acids, roughly. Histidine number 12 and histidine number 119. What I want you to recognize and appreciate about this is that this protein has taken on a tertiary structure where these two amino acids are very close to one another. So these are active site amino acids. So despite the fact that they're separated by 107 amino acids in the primary structure, they're super close together in the tertiary structure. Now, tell me in the chat, and in order to answer this question, ignore the arrows. One of these amino acids is acting as a general acid and one is acting as a general base. Tell me the number of the amino acid that is acting as the base. In order to act as a base, it cannot have a proton. It has to be accepting or ready to accept a proton. So in this case, histidine number 12 is acting as the base. Histidine 119, by comparison, as it is protonated, is acting as the acid. So that's the sort of question that I want you to be able to answer. So if I showed you something and I would take a mechanism and say, tell me about this. Which one of these amino acids is acting as an acid? Which is acting as a base, and so on. Now, all that's happening in this mechanism is histidine 12 is picking up a proton. That sets off a series of events that leads to histidine 119 donating a proton. Now, I'm not going to ask you to redraw or memorize this mechanism. The keys that I want you to understand about this mechanism is the identity of the amino acids. What is it doing? Then I want you to look at this and answer the question, yes or no. Is there a covalent bond? And look through all of these different things. Is there a covalent bond formed between our enzyme and our substrate? And yeah, yes or no? I mean, if we look at the different amino acids, we've got his12 and his119. His12 gives up a proton, or picks up a proton. This proton is lost by RNA. You're absolutely right. It does not. There is no covalent bond found between our amino acids of our enzyme and our substrate. This is purely acid-base catalysis that's taking place here. His12 picks up a proton, 119 donates a proton. Water comes in and says, oh, you need to be replenished. You need to be quenched. You need to get back where you started. Because at this phase right here, histidine 12, that's protonated. Histidine number 12, that's acting as it's ready to act as an acid. And we don't like that. We want it to act as a base. That's how we started. And the entire value of an enzyme is you can end up where you're going to start. So His12 needs to get rid of that proton. How is it going to do that? Well, thankfully, water comes in. And when water comes in, it's going to act as an acid. And it's going to donate a proton to histidine 119. That's what we see going on down here. Water is acting as an acid, donating that proton. That's going to set off a series of events that lead our substrate to extract this proton from histidine 12, which gets us back to here. His 12 can be a base again. His 119 can be an acid again. So we can do the same thing over and over and over again. What I want you to, whenever you look at a mechanism, I want you to think, what are these amino acids doing? Are they forming a covalent bond between themselves and the substrate? Yes or no? Now, the next mechanism, and if you want a video on ribonuclease A, I've got one on my YouTube channel that has like 9,000 views. And you're welcome to look at that. I can share that link if you want to kind of get a nice review of that. Nice, amazing review of that. Okay, our next enzyme is carbonic anhydrase. And I apologize that those arrows went there. The equilibrium arrow should be here. And I'm going to go ahead and say plus a proton. Now, what we know about carbonic anhydrase is it helps CO2 react with H2O to form HCO3 minus and a proton. We talked about carbonic anhydrase in the context of hemoglobin and respiration. What is happening is we got to start right here. We've got a zinc ion. That zinc ion is coordinated by 3 histidine residues that are within the active site of my amino acid, of my enzyme. So that the active site residues with carbonic anhydrase are histidine residues that basically grab onto the zinc and hold it there. Now that zinc ion, well, it's still an electrophile, so it's going to attract a water molecule because that water molecule's got some lone pairs of electrons. And whenever it does that, one of the things, and actually, could somebody add to the chat, what is the pKa of water? It's a number. 14. Perfect. What this is going to do is this interaction between water and zinc is going to cause the pKa of this specific water molecule to drop down to 7. It's going to go from 14 to 7. And what that means is that, well, it's going to lose a proton. It's going to be deprotonated. Okay, so there goes a proton. That's going to leave behind this hydroxide ion. That hydroxide ion is going to attract our CO2 molecule. Now, keep in mind, this is something that happens spontaneously without the intervention of an enzyme, but it goes a lot faster with an enzyme. This hydroxide ion can grab the CO2, and whenever that happens, it forms a covalent bond between our oxygen and our carbon, established right here. That negatively charged oxygen that results from the formation of the covalent bond is going to help to be coordinated by this zinc ion. And lo and behold, what were we trying to make throughout all of this? One of the things that we were trying to make was a proton. Done. Another thing that we were trying to make was HCO3. HCOOO. HCO3 with a single -1 charge. That HCO3 is going to be displaced by a water molecule, and we start this all over again. The heart of all of this is these histidine residues or these histidine R groups within this enzyme coordinating a zinc ion. And that drives the pKa of water down from 14 to 7. This is an example of metal ion catalysis. So we've looked at acid-base catalysis, metal ion catalysis. Our last type of catalysis that we're going to look at is covalent catalysis. Now, before we proceed from here, what I want you to ask the question of and be able to answer the question of is, what do you think the protonation state of these histidines is? Do you think these histidines, I'll ask you to say P for protonated or D for deprotonated? What do you think it is? We got a zinc ion in the middle there. Do you think it's D that these histidines are deprotonated or P that they're protonated? Got some votes for protonated. Well, let's look at it. A deprotonated histidine, what's it going to have? Here's my little histidine. Lone pairs of electrons. A protonated histidine is going to have that. It's not going to have those lone pairs of electrons, and it's going to have a positive charge. Which one of these, this or this, A or B, which one of those do you think is going to be attracted to a positively charged zinc ion? Something that has a partial negative or something that has full-on positive? Absolutely right. It's going to be the A form. So these histidine residues are going to be deprotonated in order to coordinate that zinc ion. Okay, now our covalent catalysis is summed up with the enzyme lysozyme. So this is an example. Lysozyme uses a covalent catalytic mechanism to break down to break down lots of different molecules, but primarily or predominantly the peptidoglycan layer of bacterial cell walls. So these glycosidic linkages are broken with the help of, or this is known as a glycosidic linkage. That's the name of the linkage that connects sugars to one another. So lysozyme is going to cleave this. It's going to cleave right here. Now, this name, NAG and NAM, NAG and NAM, those are the names of the individual sugar subunits. So NAG is N-acetylglucosamine. Maybe you've heard of that because you've heard of like glucosamine and chondroitin. NAM is another sugar known as N-acetamuramate. So these are two sugars that are connected with this bond right here. Lysozyme breaks that bond, and that's how lysozyme is used to break down bacterial cell walls. Now, this figure right here, what this is showing is the polymer of sugars and how it's inserted into the active site. So where I've drawn these squiggly red lines, that comprises the active site of lysozyme. We've got tryptophan, alanine, asparagine, glutamine, glutamate, glutamine, asparagine, glutamate, phenylalanine, asparagine, arginine. And in the event, and sorry about that, valine, aspartate, in the event that you're thinking, oh, sweet, we've got like 16 amino acids involved in the mechanism. Yay! Don't despair. That's not the case. What this is illustrating is that all of these different amino acids don't play a role in pushing electrons, but instead they play a role in shape, in making a proper kind of shape or pocket for our substrate to fit into. Now, at the end of the day, there are only a few amino acids that are involved. And I'm going to jump over here because this is our mechanism for our lipopolysaccharide to be broken down. Now, we've got glutamate 35, aspartate 52, and then I'm going to scroll around for a couple others and, oh no, it's only those two amino acids, glutamate and aspartate. Now, can anyone tell me what glutamate 35 is doing? Take a look at that and just say what it's doing in the chat. And ask yourself the questions like, is it protonated? Is it deprotonated? Does that matter? Miracle, Yes, it is acting as Claire. Yes, acting as an acid, it is donating a proton. You are absolutely right. Now, this is a place where it gets a little bit hairy, but I don't want you to despair about that. And again, do I want you to have all of these different things memorized? No. What I want you to focus on is I want you to look at something like this and answer the question, oh, well, based on these two steps, here's what this amino acid is doing. It's very tempting to see glutamic acid 35 protonated acting as an acid, and then see, oh, we've got a deprotonated aspartate 52 and say, I know what's happening. Glutamate's acting as an acid, aspartate's acting as a base. Done. Well, if this was all that you were given, that would be, a good answer based on the information that you're provided with. But when you go down here, then you see that, oh, well, this deprotonated aspartate, can you give me a number in the chat or give me a Y in the chat if you see that deprotonated ASP52? A Y in the chat or an N if you say, I don't see it. Okay. So we've got a deprotonated aspartate there. And oh, well, I'm going to expand my drawing a little bit. We got an arrow. So it's going for something. Is it going for a proton? No, it's not. Holy mackerel. That's a carbocation. We've got an oxonium ion there. A positively charged carbon. We've got an oxonium ion. What this aspartate 52 is doing is live it up. There it is. There it is. What is that? What type of bond is that? I'm going to zoom in so we can see it better. Boom, 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 boom. Covalent bond. Oh, too far, too far, too far. We've got a covalent bond there. So we talked about, oh, well, there's general acid catalysis. Now we've got covalent catalysis. This is all correct. These are all correct. If you're going to classify this, the classification of this entire mechanism, we would classify it as covalent catalysis because, well, that's kind of more of the story than the acid-base catalysis or the acid catalysis. Now, will I ask you to classify an entire mechanism? No. I'll ask you to look at a step and I'll say, and actually, I'll take that back. What I'm most interested in is you telling me what role an amino acid has. So aspartate 52, it's deprotonated. It's acting as a really great, strong nucleophile. So that nucleophile can attack the electrophile that's found on our substrate, establishing that covalent bond that is temporary or transient. And after that, what are we going to do? Well, we have to bring in a water. And when that water comes in, that is going to help us out because that water is going to enable us to, well, return our aspartate to a deprotonated form. It's going to enable our glutamate 35 to become protonated again so it can return to its acid state. Now, with all of that said, when it comes to mechanisms, I want you to be able to, if I give you an image of a mechanism or a step of a mechanism, I want you to tell me what that mechanism or what a given amino acid is doing within a mechanism. If you're thinking, well, how am I going to figure that out? What I would do is I would just go to Google image search and I would say, give me a mechanism that shows an amino acid acting as a nucleophile. Covalent catalysis. These are some of the search strings that I would come up with. Acid-base catalysis. I've got the RNase A mechanism. That's a good one to look at. Metal ion catalysis. Just think, okay, well, we've got to have nucleophiles that coordinate an ion. Coordinate a metal ion. And that's why it's metal ion catalysis. Does anyone have any questions about acid-base, metal ion, or covalent catalysis? Okay. Now, with where we are right now, we're going to jump ahead to proteases. Proteases, chymotrypsin is a protease. And this is one specific example of a protease that I want you to have a little bit of knowledge about. But in terms of the mechanism, again, I want you to know what that amino acid is doing. And I want you to see these different roles. So proteases cut peptide bonds. Serine proteases are classes of enzymes. Serine proteases are a family of catalytic enzymes that have an active site serine. Man, oh man, whoever was the wordsmith who came up with the term serine proteases because there's a serine in the active site, I applaud you. In addition to that, there's another class of proteases known as aspartic proteases. Does anyone want to guess what amino acid is in the active site of an aspartic protease? I'll give you the opportunity to add the single letter code for 1 bonus point on the next exam. Perfect. D for aspartic acid. There's an aspartate. There's an aspartic acid within the active site of an aspartic protease. Now, chymotrypsin and subtilisin are both examples of serine proteases. They both have serines. Those serines both act as nucleophiles. Thrombin is another serine proteases. This is just kind of a flex on get ready for what serine proteases do because trypsin, chymotrypsin, and elastase are all found in your gut and they are digestive enzymes. Subtilisin is a bacterial protease, and another, last but not least, is plasmin. Plasmin breaks down fibrin proteins of blood clots. If you've ever known anyone who has suffered a stroke, um, if you're interested in being a physician or a PA or something like that, you should probably familiarize yourself with TPA. TPA, also known as tissue plasminogen activator. That is a substance that cleaves the proenzyme plasminogen to activate plasmin. This is TPA, or tissue plasminogen activator, is a drug that needs to be administered very early after someone is experiencing stroke symptoms. I believe it's within the first 3 hours or so, because what it does is it busts clots. So the clot that's in that clot that is cutting off blood flow and oxygen to the brain, well, TPA, if administered in the right window of time, can basically make someone suffer a stroke and not really experiencing anything. A couple of years ago, I saw somebody in the hospital and they had a note in the ICU and they had on their door, it said TPA patient. They were in the ICU because they were recovering from their stroke. But this person who was recovering from the stroke, who had TPA administered, well, they were sitting watching TV because they had TPA administered within the right window of time. And within that right window of time, all that they were dealing with and resolving was the fact that they had something that was effectively preventing any sort of blood clots from forming. So that would be a problem if they like suffered a cut or something like that. But for their overall cognitive abilities and mental cognitive health, they were doing just fine. Okay. Now with that in mind, this term plasminogen, tissue plasminogen act what on earth? Oh, there's a water drop. Tissue plasminogen is that term plasminogen, that suffix OGEN, is pretty significant. And it is related to a zymogen. Zymogens, although they sound like characters from Star Wars or Star Trek, zymogens are enzymes that are inactive until they are activated. This right here is chymotrypsinogen. Chymotrypsinogen is chymotrypsin, a serine protease that is inactive. Well, it gets activated through proteolytic cleavage. This sounds a little bit weird, but this is a protease that activates itself by cutting peptide bonds. Now I'm going to move through this a little bit briskly. What I want you to know about this is that this is irreversible. So the activation of zymogens is irreversible. Why is that? Because, I'll say B/C, or because peptide bonds have been cut. I'll say been broken. Okay. Now, serine proteases exist in your cells as zymogens. So what they do is they float around and at the right time, well, they get activated and then they go around and they cut up whatever their targets are. These proteases are very selective. They cut based on a particular protein sequence. Trypsin, chymotrypsin, and elastase, they're going to cut the same bond, but only in a specific pattern. For example, trypsin will only cut after positive residues. Chymotrypsin is only going to cut after a bulky residue like a phenylalanine. Now, I don't want you to struggle with or spend a lot of time on these specificities. I do want you to know that a zymogen is activated by proteolytic cleavage. I want you to know that serine proteases have an active site serine. I want you to know that serine proteases are selective. I don't want you to know the specific selectivity, but I want you to know that they are selective. Um, and here's their selectivity, but I don't want you to stress about that. I just want you to know that they are selective. And the reason they are selective is because they have a structural part of their cells known as the specificity pocket. They have a region of the protein that complements their substrates, and based on what they bind to, they will cut that. Now, the mechanism for a serine protease, like I said, it's got a serine, but it's also got what's known as the catalytic triad. This catalytic triad is the 3 amino acids that are most critical for the active site or the catalysis done by these enzymes. The enzymes are histidine, or sorry, the amino acids are histidine, aspartate, and serine. Serine acts as a nucleophile, histidine acts as a general base, and aspartate acts the hydrogen bond. The way that I always think about this, if you've ever seen the movie The Big Lebowski, well, that aspartate, it's kind of like the Big Lebowski's rug. It just really holds the room together. That aspartate, if we look at the mechanism, doesn't actually do anything. I mean, yeah, it does hydrogen bonding, but that means it just kind of hangs out. So what I want you to know and what I want you to look at is in each one of these cells, these are the 7 steps of this mechanism. Serine, histidine, aspartate. If we look just at aspartate, in each one of these cells, it looks the exact same. Nothing about it changes. And that's because all that it's doing is it's basically holding up space for the other amino acids. Now, if we look at histidine, that histidine number 57, well, here it's deprotonated. Here it's protonated. Deprotonated, 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 protonated, deprotonated. It just goes from protonated to, or it goes from deprotonated to protonated. Why is that? Well, because it's contributing to the nucleophilicity of serine. It's deprotonated so it can pick a proton off of serine. That whenever it does that, that enables our serine to establish the covalent bond between itself and our peptide. And that is basically setting the wheels in motion to break the peptide bond on our substrate. So if you were to look at this and say, okay, well, how is this going to be a question on an exam? I'd want you to, if I showed you this model right here, number 2, and I said, well, what is serine doing? Well, serine's established the hydrogen bond between it, or sorry, the covalent bond between itself and the substrate. Then I could also ask, what's the protonation state of histidine? What's the protonation state of aspartate? Those are good questions. Now, I do want you to know specifically about the catalytic triad. You know, I could say, hey, this is a part of the trypsin mechanism. What is serine doing? What's histidine doing? And what's aspartate doing? I would want you to say, well, aspartate is involved in hydrogen bonding. Histidine is protonated, however, it is going to generally act as a general base. Those are the sorts of questions I want you to know the answer to. Now, with respect to our substrate, just for kind of not necessarily trivial knowledge, but for full context, the bond that's being broken is the bond right here. As soon as we have established a bond between our covalent bond between our nucleophile serine and the um, peptide backbone, well, then what we can do is move electrons to break that peptide bond. So at this point in time, transitioning from 3 to 4, our peptide bond is broken. We have released one of our substrates or half of our substrate. Now we just need to regenerate everything. Okay, now, does anyone have any questions about mechanisms? If there are no questions about mechanisms, which I need to drink some water, there are no questions about mechanisms, we're going to go into one of our two last items. We've got two last topics. One is enzyme regulation, and then the other is inhibition of enzymes in the Lineweaver-Burke plot. Okay, so enzyme regulation. And just so you guys know, I've got enzymes on the agenda for next week as well. So some of these things with respect to inhibition we might tackle, or we're going to tackle some of them next week. They're going to stay on this PowerPoint, but I'll grab what we don't cover this week and I'll throw it on to next week. Okay, so enzymes can be regulated in a number of different ways. And what do you think regulation means? Add to the chat, give me a definition of regulation. I like it. Well, regulation, controlling a substance. These are good definitions for regulation. Ooh, maintain balance. I like that. So, yeah, control, kind of monitoring things and kind of like yeah, what was it? Keeping things in check. Keeping stuff in check. I like that. Yeah, absolutely. We want to regulate an enzyme's activity. If we think about, for example, a protease, what could somebody add to the chat? What type of bond does a protease break? Peptide. Okay. Now answer me this and give me a Y or an N. Yet Y for yes and N for no. Does hemoglobin have any peptide bonds? Yeah. Yes, hemoglobin does have peptide bonds. Hemoglobin's a protein, it's got a bunch of peptide bonds. Um, is hemoglobin an important enzyme? Give me a Y for yes or an N for no. And for the purposes of living. Yeah. Yeah, it is. Do you think that we should regulate or monitor or control or have a sense of the breaking of peptide bonds? Or do you think that we should just set a protease loose and say, hey, if you need to cut a peptide bond, cut a peptide bond? Say Y if you're in favor of cut every peptide bond that you want and don't care, or an N if you think, I think we should kind of monitor which peptide bonds get broken. Okay, good. I'm happy to see lots of N's on that. So, proteases, what they can do is they can just go. Are there circumstances where we want that to happen? Yeah. If a cell is undergoing senescence, if a cell is, at the tail end of its life cycle, we want that to happen. We don't want that to happen all the time. So, with that as an example, that's kind of my sales pitch for enzyme regulation. Enzyme activity regulation is important. Now, how can enzymes be regulated? Well, enzymes can be regulated allosterically. We talked about the allosteric function and allosteric regulation of hemoglobin. When we favored the T state, then we were favoring the deoxy form of hemoglobin. When we favor the R state, we're favoring the oxygenated form of hemoglobin. We're favoring the active form. Now, hemoglobin is not an enzyme, but let me tell you that there are enzymes that are multi-subunit. And they both have, and they have the T state and the R state. Which one is the active state? The T or the R? Add that to the chat. R. R is our active state. Okay. Now, we talked about regulators. We talked about homotropic and heterotropic interactors. Here we're going to use a slightly different terminology, allosteric regulators. So there can be positive allosteric regulators and negative allosteric regulators. A positive allosteric regulator is something that kind of encourages that activity to go. So if you think back to hemoglobin, well, let's see, with respect to hemoglobin, then oxygen is a positive allosteric regulator because it said, hey, bind more oxygen. Now, in many enzymes, you have kind of two subunits when it comes to uh, a multi subunit enzyme. We have a catalytic subunit represented here by C. So this is the one that actually does the work. And then R as a regulatory subunit. Now, in these regulatory subunits, that is where, in this model, where a positive modulator or positive allosteric regulator is going to bind. So our catalytic subunit right here, that would be where our substrate binds. And we've got this substrate that's kind of like pizza shaped, and then we've got this catalytic subunit that, well, it looks like it will accept a square. The substrate's not going to fit right here. But when our positive modulator binds, that causes our protein or our enzyme to change shape, to transition to our R state or our R form of our enzyme. In which case, then our normal substrate is able to bind to our catalytic subunit. And that's whenever our action can actually take place. Now, over here on the right-hand side is showing a negative feedback loop. So this is an enzymatic pathway by which threonine, the amino acid, is converted to isoleucine. One of the enzymes in this pathway is known as threonine dehydratase. Well, that molecule, or that enzyme, I'm sorry, is one in a series of steps. Isoleucine is a negative inhibitor, or sorry, is a negative regulator. It is a negative allosteric regulator of threonine dehydratase. So this is kind of a mechanism where, hey, yeah, we're making a bunch of isoleucine from threonine, but we don't need any more. So isoleucine blocks threonine dehydratase. It's almost like the concentration of isoleucine is high enough that it will bind to the regulatory subunit and block the production or that reaction from naturally taking place. Now, whenever we talked about oxygen binding curves, and we looked at the oxygen binding curve for myoglobin, and we looked at the oxygen binding curve for hemoglobin, they had different shapes. Hemoglobin was sigmoidal, whereas myoglobin was a hyperbolic curve. Well, we see the same thing when it comes to enzymes. Here what we have is our normal untreated um, allosteric enzyme. Then if we look down here, we see, oh, when a positive modulator binds, that causes our enzyme's activity to increase, in which case our Km decreases, our affinity for our substrate gets higher. Whereas a negative regulator, well, that causes our affinity for our substrate to go down because our Km goes up. Now, when you look at these curves, let's just kind of imagine if we were to extrapolate out on into eternity, they're ultimately going to reach the same Km, or sorry, the same Vmax, just might take longer. You could look at this as a shift to the right with a negative allosteric regulator. This as a shift to the left. Now, our next form of regulation is known as covalent modification. Covalent modification is our second. So we've got allosteric regulation, which we have a little bit of context because we talked about hemoglobin before. We're favoring the T state or the R state. Covalent modification is where We have a small molecule that gets covalently added to our enzyme. Now, I've got 3 different examples for this. We've got adenylation. We've got methylation. Last but not least, we have phosphorylation. Okay. Adenylation is where you have an enzyme. And this enzyme, within its sequence, has a tyrosine. Nope, a tyrosine residue. If you think back to tyrosine, it looks a little bit like this. There's our tyrosine residue. And what happens to a tyrosine residue, or what can happen to a tyrosine residue, is this hydroxide group can be replaced by this right here. Just to illustrate this completely, how many atoms constitute OH? Add it to the chat. 2. Yep, great. Okay. 2 is it's more than 1. Yeah. Okay. Now, this right here. How many atoms are in that box where I put a star? Is it more than 2? Add a Y for yes, or okay. Is it more than 3? Yeah. I mean, we've added a sugar on there, and then we've added a nitrogenous base. We've added a pretty big thing on there. That's almost like, hey, I'm going to remove the bumper from my car, and in place of the bumper, I'm going to put a boat. If I were to like solder or weld a boat onto the back of my car where my bumper once was, do you think my car is going to behave a little bit differently? Thank you, Claire, for the yes. It absolutely will. So the interactions, Mila, okay. You do bring up a good point. What kind of boat? Are we talking like a little fishing boat? I'm thinking I should have said yacht. I prefer yachts. That is the only boat. That's why I don't have one. I've elected to wait until I want to buy a yacht. Okay, so this hydroxide group is gone. And instead we had this whole thing on there. Our enzyme is going to behave differently because that OH group that was, it was a little polar group has been replaced by this. The enzyme behaves differently with this covalent modification. Now, another covalent modification happens to a glutamate. Glutamate or glutamic acid is a polar negative residue. Methylation. Okay, so we've got a polar negative, and we add a methyl group. Oof. Does that change the type of interactions our amino acid's going to take or participate in? Yeah. We've gone from polar negative to just kind of like non-polar. So are we going to have ionic interactions? Nope. It's going to be kind of boring. Now, in all of these cases, or in both of these cases, these are reversible. So adenylation, that group can be added, but then it can be removed. Methylation, that group can be added, that group can be removed. Now, in many cases, enzymes are modified. They undergo these covalent modifications to basically turn them on or turn them off. The enzyme is, say it's active, but then this residue gets methylated. Well, then that renders it inactive, just as an example. And the thought on all of this is, well, it's changing the types of interactions that are taking place, but it's also making this molecule like less active. Sorry, it's taking something, it's a way of regulating it, keeping it in check. Hey, we don't need this enzyme to work anymore. Let's throw an adenylyl group on there. That's going to stop it. Maybe a more common form of regulation that you're possibly familiar with is phosphorylation. Can you give me a Y if you've ever heard of phosphorylation, or an N if nope, never heard of that? Okay. Phosphorylation is kind of the classical example of a regulatory modification. These are all post-translational modifications. Phosphorylation happens to a tyrosine, a serine, threonine, and sometimes a histidine. Now, these first three, what do you know about tyrosine, serine, and threonine? What do they all have in common? I'll give you a hint. It's a functional group. Add to the chat what functional group. Oh, yep. Thank you, Drew. You're absolutely right. They all have that hydroxyl group. Now, that hydroxyl group is polar. Serine, threonine, tyrosine, histidine, those are all, well, sorry, serine, threonine, and tyrosine are all polar uncharged residues. Histidine's polar positive. When you add a phosphate on there, that's got two negative charges. That converts that residue from being a polar uncharged residue, in the case of tyrosine, serine, and threonine, to be a polar negative residue. Now, as an example, this right here is kind of a model for regulation. What this is showing is that I just want to highlight, I'm going to scribble out what's in the middle. This is our dephosphorylated enzyme at the top. Phosphorylase B, dephosphorylated. Phosphorylase A, here we've got that phosphate group that has been added to these two subunits. The addition of those phosphorylations make this an active enzyme. Okay, so what I would recommend doing is thinking about these covalent modifications as kind of being the light switch. Is it on or is it off? Just like a light switch, they can be added and they can be removed. Or sorry, they can be, covalent modifications can be added to an amino acid within an enzyme, but they can also be removed. Okay, so now we have talked about the following. We've talked about mechanisms. We've talked about pushing electrons. We've talked about acid-base, metal ion, and covalent catalysis. Then we went on to regulation. We've got allosteric regulation. We've got activation by proteolytic digestion. Then, last but not least, we've got covalent modifications by the addition of a small functional group. I think, or what I want you to know is I want you to know the amino acids that are involved or that are the sites of addition. So adenylation, where is that bound? It's added to a tyrosine. Methylation, glutamate. Phosphorylation, what residues are possible targets for those additions? Now, the last thing that we're going to talk about is enzyme inhibition. And we're going to get through a part of this. We're going to look at some graphs, and then we're going to pick this back up again next week. So what we covered today with respect to inhibition is all that will be on this exam with respect to inhibition. We'll revisit it because it's a super important topic. I don't want to, spend the next 30 minutes just trying to So what we have talked about is a Michaelis-Menten curve. This is the way that we've looked at enzymes and how they function. And the idea of, and I'd like to share this with you guys. When I was a grad student, one of the professors that I taught for, he did this experiment in class. And what he would do is he would get 5 people, or let's just make it simpler and let's say 3 people. And he would bring them up in front of the class and he'd say, all right, have a seat. You guys are Oreo cookie lyase enzymes. That was his fun name for enzymes. He'd say, all right, well, I'm going to put at each of your desks an Oreo. And what you're going to do is you're going to pick it up and twist it. And he'd say, I'm going to put 10 seconds on the clock, and I'm going to put an Oreo at each desk, start the timer, and then stop the timer. And so he would go through rounds of this, and he'd say, okay, round 1. Each person has an Oreo, and those Oreos would basically be substrate concentration. The people are the enzymes. The number of people does not change. So the enzyme concentration is fixed. And in round 1, you have 3 Oreos. You'd say, all right, on your mark, get set, go. Each person would pick up their Oreo, twist it, be done. And then he'd go, all right, done. And so the substrate concentration in round one would be, let's see, I'm going to get my table going here all together. Substrate concentration was three Oreos. Velocity was 3 Oreos per 10 seconds. Then in round two, he'd put 2 Oreos down at each desk, 6 Oreos down total. And he'd say, all right, go. And everyone pick up their Oreos, twist. Okay. And so what he would do is he'd get, okay, well, we got in round one, 3 Oreos per 10 seconds. And then for round two, we had 6 Oreos. So our concentration went up. So we went from basically this point to this point. And he'd say, okay, well, how many Oreos were twisted? And, let's say we got 5 Oreos per 10 seconds. Let's just imagine that one person, fumbled or something like that. Round three, he'd go with 9 Oreos. Round four, he'd go with 12 Oreos. And then round five, he would continue on. He'd be adding more and more Oreos. And as the number of Oreos would increase, what would happen to the velocity? What would happen to the rate? Well, that would go up. And let's say in round three, let's say you got 9 Oreos per 10 seconds. Then around four, let's say you got 11 Oreos per 10 seconds. Round five, for simplicity's sake, let's say you got 12. Round six, let's say that we put 18 down, but only 13 Oreos got opened up. Round seven, the number of Oreos, the velocity, the y-axis here would kind of taper off. So yeah, we added more and more Oreos, but there's a breaking point. One person can only, take care of so many Oreos. So our Michaelis-Menten curve here, and looking at this equation, I've got this question for you. Is that data linear? Answer in the chat, yes or no. The graphed data there. Let me erase some of my markings so I see a little better. No, it's not. It's not. So, on a scale of 1 to fun, where would you rank nonlinear data? I would rank it a 1 because I personally am like, it's not so fun. Linear data, on the other hand, I like that. Because I remember in fourth grade, Mrs. Rennick's class, we learned about the equation for the line. Y equals mx plus b. That's the equation that we learned. That is a great equation for linear data. It's predictable. Now, the great thing is that we can take Michaelis-Menten data or the data, and we can modify it to give us y equals mx plus b. This is known as a Lineweaver-Burk double reciprocal plot, and it gives you that relationship. To make this plot, you take the reciprocal of your y-axis data. Then you take the x-axis data, and you take the reciprocal of that. So if on a Michaelis-Menten plot, you have an x-axis value of 2, 1 divided by 2 is 0.5. And that would be the value that you would put down. The x-axis data on a Michaelis-Menten curve, take 1 over that, and that is the x-axis data for a Lineweaver-Burk plot. Now, your new plot, your new graph, has 1 over initial velocity, 1 over v, and on your y-axis, and your x-axis is 1 over substrate concentration. Now, looking at this Lineweaver-Burk plot, here it is. One of the things that I want you to be aware of and look at is this is our label for our y-axis. This is our label for our x-axis. This right here, 1 over v max, is our label for our y-intercept. And this right here, this negative 1 over km is our value for our x-intercept. Now, what this shows is when you do a Michaelis-Menten plot, what are you doing with your Vmax? You're making an estimation. And by that estimation, then you have to make another estimation about your Km. when you prepare a Lineweaver-Burk plot, you make something that is quite a bit more predictable, and your answer is going to be a little bit more finite and more defined. Because you can take y equals mx plus b, and you would, sorry, whenever you plot that data, you will get an equation that fits y equals mx plus b. And then you'll say, oh man, what is the, when will, how do I find out my y-intercept? Your y-intercept is going to be the value when x is equal to 0. Because remember, this is a coordinate. This is an x, y coordinate. So your coordinate would be 0, comma, and then whatever that is. Let's say it's, 3.2. That would be your y-intercept, 3.2, and then you'd say 3.2 equals 1 over v max. Your x-intercept, well, that would be also an xy coordinate. But that would be where y equals 0. So you'd say, negative 4.1, comma, these are the xy coordinates, comma 0. Well, negative 4.1 equals negative 1 over km. Do the math to solve what km stands for, or km is equal to. Could anyone solve for, I want one person to solve for my Vmax and one person to solve for km based on these two equations, or based on these two values that I plugged in, just for funsies. I'll do it as well. Add it to the chat whenever you get it. One divided by 3.2, 0.3125. Awesome. Miracle, 0.24. You're absolutely right. Miracle, I noticed that you have 0.24 as opposed to, but what, let me ask you, and anyone on this one, should the km be a negative value? No, it should not. And if you were thinking to yourself, oh, maybe there's some substance to that question that he just asked. Has anyone ever, in any lab that you've ever been in, have you ever been asked to prepare a solution that's like, hey, go make a negative 6.2 molar sodium chloride solution? Answer yes or no on that. No, got some no's. Yeah, that would be kind of impossible. You can't have a negative concentration of a solution. So a km, after all, is a concentration. I just want to bring that up because that's a kind of common pitfall for folks. Okay. Now, this Lineweaver-Burk plot is important because it is a foundation for enzyme inhibition. An enzyme inhibitor is a substance that reduces an enzyme activity. There are two types. There's irreversible and reversible. Irreversible enzyme inhibitors, these are also referred to as inactivators. They bind to the enzyme permanently. They chemically modify an enzyme that is critical for that enzyme to function. We focus predominantly on reversible enzyme inhibitors. Typically, they have a site on the enzyme that they bind to, and then they release from it. And sometimes they compete for the binding site of the enzyme. Now, when it comes to inhibitors, we're going to focus on our reversible inhibitors. There are 4 types of inhibitors, and the first one up there is the one that we're going to focus in on. And this is the only one, yeah. We're going to talk about the competitive inhibitor, then we're going to call it a day on inhibition. The rest of them, non-competitive, mixed, and uncompetitive, will be booted until next week. Competitive inhibitors. A competitive inhibitor competes for the substrate binding site. So if the substrate binds in this location on this particular pocket, a competitive inhibitor will bind there as well. And when the competitive inhibitor is there, the natural substrate cannot bind there. Now, with that in mind, what does that look like? Because after all, when it comes to inhibition, that's what we want to be able to answer. So competitive inhibitors, all the notation that you saw here, we're going to deconstruct all of this when we look at every individual inhibition or type. A competitive inhibitor. Well, the enzyme cannot simultaneously bind the inhibitor and the substrate. They will compete for the same binding site. In the case of competitive inhibition, of our two kinetic parameters, Km and Vmax, Vmax is unchanged. Km will, however, change. Now, if we look down here at a Lineweaver-Burk plot, this bottom plot, our y-intercept right there, what we want to focus in on is our different lines. Here, here, and here. This line, that's kind of an olive green colored line, represents enzyme activity when no inhibitor is present. This bluish line represents when an inhibitor is present, and then this purple line represents when an inhibitor is present and the concentration of that inhibitor is even higher. So this and this line denote different amounts of an inhibitor. This shows that a competitive inhibitor will cause the y-intercept to remain unchanged, which means the Vmax is unchanged because 1 over Vmax is unchanged. So in the presence of a competitive inhibitor, the enzyme will ultimately get to its highest rate. But what else changes? But how? Why? Huh? Is it doing anything? Well, yes, it is. What it's doing is it's changing the Km. Okay? Now, think about that. The Km is the concentration that of our substrate that our enzyme needs to get to half of its maximum velocity. Tell me in the chat, do you think that the Km will go down or will the Km go up in the presence of a competitive inhibitor? Will you need more or less? Guys, this is awesome. Your Km goes up. What does that mean for your enzyme's affinity for your substrate? Goes down. So this is commonly referred to as the Km apparent. Km goes up. Vmax is unchanged. A competitive inhibitor causes the Km to go up, meaning you need more and more of that substrate in order to get to your maximum velocity. So I always kind of think about it like, well, I'm just going to stop there. Up here is a Michaelis-Menten curve. What we see is this olive one is unchanged. Blue is with the inhibitor, and then the purple one is with even more inhibitor. If we were to extrapolate this out on into infinity, if we wanted to take that into infinity, what we would see is that these lines right here, they ultimately do reach the same point. It just might take for what seems like forever. Now, a schematic representation of a competitive inhibitor is shown here. The free enzyme has two options: combine the substrate or combine the inhibitor. And if it's got one substrate and one inhibitor, it's almost 50-50. Flip a coin, what's it going to bind? Well, how can we increase the odds that our reaction is going to take place? Increase the concentration of our substrate. which is at the heart of this competition. Now, in the event that the free enzyme binds the inhibitor, we'll form a complex known as EI. If the enzyme binds to the inhibitor, EI will be formed, ES will not. ES will be formed only if the enzyme binds to the substrate. So what I want you to know about these curves is I want you to notice that the Lineweaver-Burke plot, as your substrate concentration as your inhibitor concentration increases, what happens to the slope of the line? Well, the slope increases. What happens to our Km? Our Km goes up. Now, this shows us basically some examples of, well, inhibition, kind of a visual. Here's our substrate and here's our enzyme. Here's the inhibitor and here's our enzyme. Well, if our substrate binds, well, then our reaction is going to take place. If our inhibitor binds, well, then our substrate can't bind. In many cases, the competitive inhibitors are what are known as substrate or transition state analogs, in that they look like the substrate or the transition state of your enzyme. There are some drugs that are also some compounds that are product analogs. These bind, but they are not going to cause any sort of reaction to take place. Now, what I want you to focus in on for competitive inhibition is I want you to know the Michaelis-Menten and the Lineweaver-Burke plots super well. I'll say that because you're going to have questions on your quiz that pertain to competitive inhibition kind of in a general sense, as well as competitive inhibition and how these plots change. Now, that is where I'm going to stop today. I've got your lectures for tomorrow. They are recorded. I have to post them. And I might not be able to post them until this evening, but I will try to take care of it right now. And that's what I got. This is where we're going to stop. Slide 56. Tomorrow's stuff is nucleic acids. Friday's stuff is sugars. I won't be available for office hours tomorrow. If you have questions, please email me. We can set up a time possibly this weekend or something like that. Other than that, though, I hope you have a great day. And if you want to talk about your test or anything like that, if you've got questions about it, please email me if you have specific questions like, hey, I thought this was this. But if you want to set up a time, let me know, and I can do that with you. All right. Well, I hope you have a great day, everyone, and I will see you next week.